Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the NPTEL course on groundwater hydrology and management. This is week 12, lecture 5. We have come to the last lecture of this NPTEL course, and I really hope that this journey that you took in the course has sensitized you on groundwater hydrology, created an awareness of what are the parameters involved in groundwater management, and the data that is needed. While speaking about data, that is what is the focus for our lectures in the current week and the last week. So we will focus again on this little bit on the data part. What do you do with all this data? And then slowly finish off this lecture and the course together. So what we have seen is there is a lot of data that comes into the database because we have started with a less understanding of groundwater hydrology. Then we establish the water balance from which you collect different data and put it into the water balance. But the water balance is a time stamped event. For example, if you say precipitation, it is an annual precipitation or monthly precipitation you use. And then you use a monthly groundwater level, monthly ET, monthly soil moisture, etc. What has happened is there is no connection between this timestamp and the next timestamp or the previous one, right? T equal to 0, T minus 1, or T plus 1. So this is where you are in need of a simulation model that can capture all this data and then evolve, automate from one timestamp to the other. But before that is done, there is something called a conceptual model. Conceptual model aggregates all the data that you collected from the field into one pictorial diagram. And from the picture, you do get a better understanding of what is happening in the real life scenario. Because, for example, you look at groundwater level and quality separately in a database. When you bring them in a conceptual model, then you understand, the groundwater level is declining and the aquifer type is changing as the groundwater level declines. And that is why the groundwater quality is bad. Unless you bring three data sets, already I said, water level, the aquifer type, and the water quality. So unless you bring all these three different data and marry them together as one conceptual model, it is difficult to understand what is happening. And that is what the conceptual model helps in clarifying by bringing all the data together. So we have collected hydroclimate data ranging from rainfall, and I've shown you about temperature, wind speed, and other things, but rainfall, storage, river discharge, soil moisture. We've looked at data on geological conditions from the lithograph and borehole data, which include your stratification, layering of your aquifers. And also we looked at high permeable, low permeable rocks, solids, etc. Porosity. All these comes under the geologic conditions because it is the base rock that actually disintegrates into soil. Okay, so when it disintegrates, you have the porosity and other things formed, and sedimentation also occurs due to geological influences. Then we had collected groundwater, which is level, the groundwater level, before which we collected the climate and the geological setting, the layering of the aquifers. Then groundwater data is collected. So we set up the water budget, didn't we? We just said, okay, this is the water level. We also use grace here for a small example. And then we said for rainfall, for the ET losses, the storage is declining or increasing. Okay, so that is what we set up as a water budget. But the water budget was only for one timestamp, and it is not giving us a full picture of a longer time series. More than the time series, how do these data react or interact between each other is not clear. Okay, for example, how much of rainfall is actually getting into the groundwater, and how much of that groundwater is going into base flow. All these need to be calculated, and that is where a model actually helps to break these boundaries and then bring them as one entity. For example, water which comes as rainfall is the same water which infiltrates, pushes the water into pore space, and then goes into the groundwater aquifer, comes back to base flow, etc. But we need to keep a check on that water always so that we know the volume and movement of water, right? So conceptual models are starting point for models. We use them as a leverage point where you start using them for uh, understanding or setting up a hydrological model. Any groundwater model would ask for a conceptual model starting. This is very similar to how you learn to solve physics problems and mathematics problems, right? When you are taught these, what do they say? Read the question, take the data from the question, and draw it. For example, you have a train moving 100 kilometers per hour. How many stations would it pass before it stops in a zero speed? Those kind of questions. Or cannonball is fired, and with a particular velocity it goes, and then it makes a trajectory and falls down. And what is the energy differences at each stage? So you would draw it, you would draw and then angle and all these things. So similarly, when you collect all this data, you create a conceptual model which can be used to better understand the need of the model. Let's take an example here from the SWOT database. Okay, so this model is actually taking all the data from different sources. For example, DEM is your elevation data, how your elevation changes influences the rainfall conversion into runoff, and the runoff going into as infiltration and groundwater. So that changes based on the slope and angle of the slope. And then you have your land use map, especially it influences your groundwater recharge, infiltration, and ET. Because if there's more ET, there is less water going in and less water stored in the groundwater. We're just going to focus on the groundwater storage as is a groundwater class. Then you have the soil map, which can be of different soil types in a given location. And every soil would behaves differently for a particular slope and rainfall. For example, there are some soil which are hydrophobic, which actually do not repel water, right? So if you have such a soil, your model will say no, water should infiltrate, but it doesn't infiltrate. So these kind of things are built in the model when you have data for it. And last, of course, your weather models, etc. So all these can go into a database. SWOT is kind of it's a hierarchical model for surface water, but I'm just using this diagram here because it gives a clear picture of you collect all this database together, pile them up, and then give it to a SWOT database. So for you, it will be a groundwater database. And then some parameterization happens, some calibration happens. You tweak the parameters, you tweak the hydrologic conductivity, the permeability, the thickness of the aquifer, all these parameters you tweak. And then finally calibrate the model and validate the model. you'll get outputs as a layer or output tables and chunks. So where does conceptual model come? Okay, so does it come here? In a surface water model, as I said, it's not much necessary, but for groundwater models, it is necessary. Let's take an example from Chinnasamy and Pratapa 2016. What you see here is we collected different ground realities and aquifer types from bore logs. Okay, so we take, for example, distance and a depth. So for a 1 kilometer radius, for example, we have taken all the locations of the borehole, and we know that when we drill the borehole in this location in Mukteshwar, there was gneiss and then some phyllite, quartz, and then bedrock. Okay, so there were different layers, but whereas in Mayora it was only one or two layers. So this was, for us, it was easy to differentiate because we had this location of the logs, and then we put it in a diagram where you have the axis as the depth. Okay, from zero level could be the bottommost zero, and from there the bedrock, you can build up the elevation profile and how the aquifer material changes. And also with some rainfall and river network, we know that water flows down and forms into a stream. So water from here comes down, and Mayura also comes down to this drainage point. And how that drainage point looks down is also a question where there's a lot of interactions. This conceptual model example is purely given to show you only about the geological setting, not much, because this is what you would then think within yourself and say, should I have 4 layers or 3 layers in my model, etc. So for example, if I know that here there is only 2 layers, and then just 50 meters, 100 meters out, I have 3 to 4 layers, then what happens is there is a dilemma how much layers I want, or can I simplify all of this into one layer? And that is what happens in a conceptual model. Initially, you put everything in the paper and you draw the model. Then, when you want to export this finding into the groundwater model, the next step. So, the first step is data collection. Second step is creating the conceptual model. And third step is converting the conceptual model into a simulation model. So this third step is where your inferences from the conceptual model will help. The most important inference is how many layers. Looking at this geology type, we could clarify that, oh, there is some differences in the layers, so let's club them, because there's not much difference between a gneiss and a phyllite, for example. It's an example, and I'm saying that if there is not much difference, then I club both of them as a gneiss. Okay, GNEIS is gneiss. So what happens here is you are clubbing layers. Why would I club layers? Because the model runs faster. You have less anisotropy and heterogeneity to account for, because you assume that all are same. So now the model would be more homogeneous and more isotropic. So your parameters also would be shared between these two equally. And that could be a good point for the modeling part, because the models take a lot of band space, like a lot of computing power, and also it may crash if it is too much layers, because there's too much interactions. You want to simplify. As I said in the modeling part, you can make a model as complex as possible to mimic nature, or you could make it less complex, simplified, but run well. So that is where you have to have a balance and give and take policy, so that it's a win-win for everyone. Okay, so think about it. But this conceptual model does help you in thinking that way of where should I put my recharge structures, where should I put my layers, how many layers, and even monitoring stations for that aspect. Let us look at another groundwater model, conceptual model, where you could see that water is flowing from top to bottom. The stream is flowing, and while the stream is flowing, some water is being lost into the banks, river banks, and then it comes back. Okay, so this is kind of a losing stream and then gains downstream. Okay, so when the water comes here in the top, let me put the pointer. Yeah. So when water comes down, you see that the part of the stream is losing water because the water goes into the ground part and into this ground part. Both the sides the water go, and that is being recorded in the wells that have been kept 3 meters away from the river bank. Okay, or the river wetted perimeter. So 3 meters, 2 meters. So there are 3 piezometers, and the depth of the piezometer is through 3.58 meters, and you have a screen size of 0.76 meters to just think about one layer they want to monitor. So here's a point: water goes in, mixes with the groundwater aquifer, and then comes back out here as a gaining stream. So this analogy and hydrology could be understood well when we draw it, because when I draw it, I know there are trees. I can put the specific tree types and how much water they would take. Thereby, I am planning well ahead on the water uptake of the plants and the water quality change, because when water goes into the ground, it gets filtered out, and when it comes back out, there is some better quality of water. So this aspect can be learned from the groundwater conceptual model. And now when I put it into the modeling sphere, where you have, for example, ModFlow simulation model, you would notice that my understanding would help in putting some parameters in the model and also fine tuning the results when I know it's not happening. For example, if the gaining and losing phenomena is not caught by the model, the simulation model, then it's asking me to change the river discharge or the well height. Then I will say, no, that is not possible, because as per the conceptual model and as per my first field work, the field and conceptual model, this is not correct. At the end of the day, the model is still a model. It tries to mimic nature. It cannot mimic fully. So you are the best person to tell the model what is right and wrong, because you will be having, for example, a field visit, and you would have seen the recharge and discharge zones in the field. So you will be in a better position to tell or fine tune the model. So this is the example of conceptual models. And these conceptual models are then fed into a modeling software. After the conceptual model setup, models are run in a 3D environment. Some models are 1D, but nowadays, because computing power is available, free open source models are available, 3D is kept. Because in a 3D, you also look at the spatial lateral movement and downward movement along with the 3 axes. Okay, I showed you the 3 axes. For example, you would have it like this. Okay, so one going down, one going X and Y, right? So, but the X and Y may be similar to each other, so you can make it 2D or 1D if only one vertical you want to look at. It's all simplifying your model depending on the data you have and the complexity you want to show in your modeling exercise. However, 3D is better, and 3D is the best because at least it gives you the 3-dimensional availability and shows how water can move from X plane to Y or Y to Z, and then from vertically to laterally and vice versa. So for all this, I would support to run a 3D model, which is a higher advanced level of groundwater management and understanding. So let's see how a 3D model is set up. First, the conceptual model is done. Okay, as I said, your field work is taken, your data collection is put in, and here you see in a mod flow setting. Mod flow is what I'll be using to show you, which is called modular flow, and that is one of the leading groundwater models in the world because it is open source and a lot of people use it, and a lot of forums are there to help you out with mod flow. It's a very good model that can actually simulate groundwater hydrology based on your inputs. So what is the first thing I said? It's a conceptual model where you have agreed to tell the model that it is only 5 layers, 1 to 5, and all of them are equally spaced, which never happens. Even a cake layer, you see it's not the same thickness everywhere. But that is what this model is saying, or at least visually, that it is the same. And there are different widths given here for the layers. Then once you set up the layers, then you put where the wells are. Where the wells, because the wells will give you the groundwater level in the layer, right? So then you divide your boundary into grids, and each point in the grid either has data or doesn't have data. So you can choose the size of the grid based on your data availability and how fine you want to see the model. Again, understand that when you over parameterize it or over grid the model, then it takes long time to run, and sometimes it is not needed to do that, right? So each grid I'm taking out. So this is the mod flow grid as columns and rows. I'm just taking one single cell out. So how does any model the groundwater flow is? For that one cell, it will look at how much is incoming, outgoing water, and then based on the soil type and the demand and the cone of depression, the water movement is given. Either it moves X direction, Y direction, or Z direction, and what is the velocity. Based on the velocity, the other neighboring cells get activated, and then the water comes in from the central grid. So this is how one water moves from one grid to the next grid. We discussed about water coming from precipitation into the ground, into the aquifer. Something similar here is happening, but there are other parameters also working at time t equal to 0. So at time t equal to 0, suppose my water is in the center block, and at time t equal to 1, it moves forward to this block. Okay. And like this, it moves, the movement is monitored by the modeling software. And at the end, it gives you the net moving velocity, the net direction, and the volume change because of this movement. So this is how a paid version of ModFlow looks like. It is called the GMS software provider. And you could see on the left-hand side, there's all these data that can come in and put on top of this model, including groundwater levels, the thickness of the aquifer, rainfall, evapotranspiration rates from your cropping calendar, etc. What you also see is they have reduced the number of wells when the family is around, but the other regions is having 1 or 2 more layers, right? So based on the data, the number of layers is fixed, and from the conceptual model also. But again, as I said, in the upper elevation regions, you can see some other layers happening, but it doesn't make much difference because there is not much water movement on top. It may be assumed to be of one particular type. Let's look at some of the results that comes out of a groundwater model. You can look at as a 3D vision to see how the water moves in and out, or a planar 2D. So this is a 2D plane top. So from the top, you're looking at the model. And what it says is there is a hydraulic head high on the north, and then there is a movement due towards the south, 2010. This is kind of 5 years old, but the science and information is still the same. You set up the model, you give it rainfall and other data, then you see how the water moves from one cube to the other. And that aggregate movement will give you the hydraulic head distribution or groundwater level recorded in the WRIS website. So what you see here is a hydraulic head is formed, and then it slowly moves down from north to south. The river flows. I didn't put the river network in because that would kind of not show you the grids. So you could see the grids as boxes. So normally it is not a box; it is an uneven surface, right? So groundwater moves from top to bottom, and then suddenly in this point within the medium range, which is green, you see some red regions, and those could be because of the how much you spend, how much you get from these countries, and then water just comes down. You could see that there are some piezometers also monitored by different faculty. So all faculties can take part in a result and change it to based on their research question. Okay. Right. And what we see here is a seasonal difference. So that is where the timestamp comes. You see water moving from north to south, but then water also moves along the region, along the time scale. So from November to February, May, and August, you see a different change in the groundwater movement. You can see the hydraulic head, high head varies, and there are some localized hydraulic heads created because of the ecosystem that is working in that region, which is trees and rocks, which enable more infiltration, and then losing and gaining streams, right? So basically, this is just to show you how a groundwater model will give you output and what you could use the groundwater output for. So with this, I would like to conclude today's lecture, and in fact, it is the last lecture of the series, where we looked at a very important part of groundwater hydrology and management. Mostly, the hydrology was understood using the scientific background, and some management scenarios were discussed where both the government and the public can have a win-win situation, not exploiting groundwater alone. Remember that for the agricultural productivity increase in India, groundwater played a very vital role. And so we need to respect and conserve it so that our development is sustainable. We have analyzed key concepts in this 12-week extent. And we also expressed or analyzed more focused groundwater relationships and analyzed different concepts on groundwater quality, groundwater availability, and how they mix and match between each other. We have established groundwater budgets. As I said, the groundwater budgets could be very, very complex or simple based on the data that we have. And since we have had good data in the recent years, there are good budgets that will be set up. Once you know the groundwater budget, it is as important to let the budget move, for which you need groundwater parameters. So for example, if you have a water level in a well, unless you know the hydraulic conductivity around the well, the water cannot pass. It will just be stuck inside the well. And this you could see most probably in large dug wells because they will be cemented on the sides, or there will be big rocks which prevent the water from moving. So once the water budget is set up, the key groundwater parameters are analyzed: hydraulic conductivity, thickness, specific yield, retention, etc. Then we looked at where can we get these data, which kind of platforms that we can use. And WRIS website has been very helpful in giving the groundwater data, which is monitored by the CGWB. So now the CGWB is giving water level data and location. Using the location, you could create a conceptual model based on the data you're having. And from the data and from your conceptual model, there could be multiple new revelations you can take, or refine your research question to answer a very focused discussion or focused groundwater problem. So I hope that this course has led for a better understanding of the conceptual part of groundwater and groundwater movement, which constitutes groundwater hydrology. Please remember, India is the highest groundwater user in the world. So there is always a need for better groundwater managers and capacity built on groundwater conservation. Conservation happens with better understanding, which can lead to better management and sustainable use of groundwater. Again, there are multiple more data and parameters that need to be discussed, but for a beginner's class, I think we have covered very lot, and I hope you use it well for your exams, and most importantly, in your future situations where you have to address groundwater. With this, I would like to conclude the final lecture for groundwater hydrology and management in PTL course. Thank you all.